Welcome. Today I'm going to talk to you guys about a specific type of measurement that we make in physics. It's kind of all over the place, and it's something that we've talked about a little bit before, but I want to try to dedicate some time specifically to this, and that is vectors. Vectors are not terrible, they're not difficult, but they do have to be handled in a slightly different way, more geometry than algebra a lot of times. But we'll get more into that when we get into two-dimensional vectors. We're going to keep things as simple as possible with one-dimensional vectors for now. Okay, with that, we're going to go ahead and get started. As I said, today's topic is vectors. It's video 13. Well, let's jump in. So the question is, why do some motion measurements require a direction? Well, you can imagine that if you are driving along the road, okay, so you're driving along the road like so, and you spot a brick wall in front of you, like so. Okay, so your car speeding along. The diagonal lines show me that it's speeding. Ooh, yeah, there you go. So speeding along with a velocity. Oh, excuse me, speeding along with a certain speed. So it has a certain speed towards the wall. And so the question is, if I hit the brakes, or if I hit one of the pedals, let's say, it's going to provide an acceleration. Those two pedals in an automatic transmission car, the two pedals each provide a certain kind of acceleration. One provides a negative acceleration and one provides a positive acceleration. You would better hope that you hit the brake that applies the negative acceleration, because as this velocity, or the speed, excuse me, is positive, making it a positive velocity, you really want to decrease that speed, hopefully in time before you hit the brick wall. So the question that I would ask is, if you're wondering why some motion measurements require a direction, the answer is because the direction will make a big difference in certain situations. Like, for example, this particular situation. Obviously, you have a motion to the right. You need an acceleration to the left to stop that motion. So that makes a big difference, right? Now, uh, there are plenty of examples of this, and we can go on and on and on about why we need it. But I think you can see just from this that analyzing your motion is really going to have to take into account the fact that you have the potential to go in different directions. And so that's where we're headed. So let's take a look up here. My next question is, what's the difference between speed and velocity? Well, speed, like for example what you measure on a speedometer, right? I think most people's cars, you have a gauge that looks like this, and it tells you what the speed is at any one particular time. We'd call that the instantaneous speed. It might be something like 40 miles per hour. Now, a speed, as we said before, is important information, but it's not enough information. And so really what we would like to have instead is some kind of gauge in your car, and some cars actually have this, where you have something that measures your speed, but then also a compass that tells you what your direction is. So let's say northwest, something along those lines. In that case, you'd have a velocitometer because it measures the velocity. I think velocitometer is kind of a cool word. It sounds like something you might find in Jurassic Park. But that's what it is. Whoops, ER, there we go. Velocitometer, that's weird, is not a real thing. Nobody says that, or at least very few people say that. So we say that we have a speedometer all the time, and so that's what people use. And even if they had this in your car, you'd still probably call it a speedometer, even though it's actually measuring the velocity, because it's giving you the speed and the direction together. Now this illustrates the point that there are two different types of measurements in physics. And this first one is a scalar, And really, scalars are what you've measured all of your life. They're numbers with no direction. And you might remember the fact that speed specifically is a scalar because they both start with S. The other type, and this is the newer type, the geometrical type of measurement, is called a vector. And vectors have to have a direction. For example, velocity. And so the velocity, which is the part of this here, starts with v, and vector starts with v. So that's how you can remember the direction. Velocity needs a direction. Velocity is a vector. There are lots and lots and lots of types of scalars and lots and lots and lots of types of vectors. So let's take a look at what that looks like here. I'm going to make a quick chart here. I'm going to give you an example, and I want you to predict where it's going to have to go. Okay, so time. Time is a great example. Does time require a direction or not? I think you can imagine that I can say 5 seconds and you know what I mean. I don't have to say 5 seconds up, right? So time is a scalar. Hopefully that makes sense. Okay, what about temperature? Temperature, does it need a direction or not? It's kind of a tricky one, right? Because oftentimes we'll say it's 45 degrees above zero or 20 degrees below zero, which sounds like it's a direction, but in reality it's not a direction. And so the answer to that is that temperature belongs as a scalar, especially temperature in physics, which is measured in Kelvin, so there's no negative numbers. What about mass? So mass is not weight. It's very different than weight. Mass is the number of particles that you have inside of your inside of an object or inside your body. Would that need a direction or not? In reality, mass does not need a direction because the number of particles inside your body doesn't have to have a direction. So we put mass here as well. Now I want you to compare that with something like displacement. Now displacement, you have to be able to tell me where you're going. So it's not enough to say you moved 5 meters. You have to say you moved 5 meters north. So displacement is a vector. Okay. We also talked about speed and velocity, so I'll put those in there as well so that you remember speed and velocity. And now the question I would ask you is acceleration a vector? If you recall from the last drawing, it was very important whether you had a positive acceleration or a negative acceleration. Those are both directions. And so acceleration, you find, is a vector as well. What about force? If you push something, can you push something in no direction? The answer to that, of course, is no. So force is a vector as well. And then the last example I'm going to use is momentum. So you can talk a lot about sports momentum, but let's imagine that we're talking about the momentum in a collision between a car and a wall. Is the car going to have a certain momentum in a direction, or is that direction not important? The answer is the direction is important. If you're in a collision, which direction your car has momentum is going to make a big difference for where the car ends up and how much damage it incurs. And so momentum is another type of vector. And so you can see that we have lots of different types of examples. I'm just going to put moment there, but you get the idea. That's momentum. So we have different examples of scalars and different examples of vectors. When you have scalars, you can add them using algebra. When you have vectors, especially if they're in 2 dimensions, you have to add them using geometry. And so if you were not a big fan of geometry, I'm going to apologize now. If you were a big fan of geometry, this is your moment to shine, because vectors all have to be added using vector geometry. So hopefully that makes sense to you. Okay, moving on. One more slide here. What are the ways in which a direction is indicated? Well, I want you to take a look at what a vector actually looks like here. Let's imagine for a moment that we have a bug, Physicists love talking about bugs, specifically ladybugs. I don't know what it is, but you will always find that physicists talk about where ladybugs are located, how they move, and so on. So let's imagine you have a bug on a flat surface. I'm going to choose my reference point to be where I find the bug initially. So it's going to be right there. If I come back later on, let's say after 10 seconds, and I find the bug is here, I will know that the bug has moved. Nothing earth-shaking about that, right? So now this is delta t, what did I say, 10 seconds. There we go. And this is where it is after I notice it after 10 seconds. So let's imagine that this is 20 meters away. It's a pretty fast bug. There we go. So it's 20 meters away. Now here, this is the 0 mark. So we will see that, actually I should say x sub 1 here. Let's make this x sub 2. So, because that's where I notice it the second time. So my question for you is, how can I indicate where it moved? Well, I can draw it as a vector. And so this is a displacement vector, like so. Okay, and it's a displacement, so I'm going to say it's delta x. Now, the length of the vector, as you can see, goes from 0 to 20, in this case positive 20. And so the length of the vector is going to be the size of the measurement. So that's 20 meters is the length of the measurement. Now, the arrowhead, you can see, points in the direction that the vector is going. The tail of the vector sits where the object started. So here's where the object started, right there at that tail, and here's where it's going. That's the head. So the direction is indicated by the way that the arrow is pointing. And so we say a vector is actually that thing. So I'm going to draw it by itself so you can see this here. So a vector would be like this. I don't have to draw the rest of that stuff in there. I just have to draw the vector. And the vector would be a displacement vector, so that's delta x, is equal to 20 meters. Do I have to put the positive 20 meters in there? No, I don't. The reason is because I'm showing the direction in the fact that I've drawn out the arrow. If you do a good job of it and you draw the arrow exactly to scale, it will help you with some of your vector addition that you have to do later on, which is something we'll talk about later on. So vectors are drawn as arrows. The length, again, is the size of the measurement, and the direction is the direction in which the vector measurement is heading. In this case, a displacement is heading to the right. You could have a speed that's heading to the right, or an acceleration that's heading to the right, or a force, or a momentum. All of those things are vectors, and all of those can be drawn using an arrow. Again, it's important to draw the arrow to scale, because later on we're going to use that scale to be able to do some simple geometry with it. Hopefully that makes sense. In one-dimensional problems like this, in other words, the bug can either go to the left or to the right, I could also just say positive 20, as I've been saying, or if it's going in the opposite direction, negative 20 meters, and that would be just fine too. So as long as it's only a one-dimensional problem, you can get away with that. That's totally okay. Positive and negative mean right and left. That's okay. But if it's not that kind of a problem, then you have to make sure that you're using the arrows like you should. Next unit, we talk about two-dimensional vectors, and so we have to always draw the arrows, whether it's horizontally positive or vertically positive, whatever. We still have to draw the arrows for it. So it's a good idea to get used to it. Okay. With that, I'm going to thank you for watching. Don't forget to do the note sheet and fill out that interesting question form. This one should be pretty straightforward, but if you have questions on it, certainly please make sure that you ask. Let's have a good discussion with it, and we have some pretty easy sample problems where I'll show you some simple math with it later on. Hopefully that helps. you have any questions, let me know. You can always email me if you have anything that's pressing that you need to get answered right now. Otherwise, we'll talk about it tomorrow. Thanks.